In this tutorial, I will show you how to model a single phase grid connected PV array in Simulink. Okay, so in this video, I will use um, solar PV array and then MPPT controller and then single phase grid. Okay, in the previous video, I showed the same single phase grid connected PV array because but in the previous video, I used the boost converter then MPPT controller, then inverter. Okay, which is called the two-stage grid connected PV. Okay, but in this video I'll cover the single stage grid connected PV array single phase. Okay, so here in this video I will not use the boost converter. Without boost converter, I will convert the single PV array DC voltage to grid connected AC. Okay, so let's start making the model. Firstly, we need a power GUI block, and its simulation type will be discrete and sample time will be TS power. Okay, so I have already assigned TS power in the workspace. You can check here. TS power is 1e minus 6 and TS control as 1e minus 5. Okay, okay, now we need PV array. Okay, for irradiance, I'm taking a constant value at first, and then I will use star generator block for the variable irradiance value. It will be 1000, and temperature I want it as 25. Okay, now we need a DC link capacitor. For that we have to take series RLC branch, and it will be C, and its value will be 3000 E minus 6, and we have to set initial capacitor voltage as 420. It's okay. Control R, and we have to set the PV array parameter, and I want to use parallel string as 1 and series connected string as 40. Okay, and module I want to choose it as 240. Click apply, and it will give us the maximum power at 100 radians is about 3.4 kilowatt. Okay, now click OK. It's okay. Now we have to take go to block to get the measurement from the PV array. Okay, so it will be MEAS or measurement of PV. Okay, and click OK. Then we need a voltage measurement block. Which is in this two-stage grid connected PV array, or sorry, it will be go to block, and it will be VDC. Okay, so it will be global, and click OK. So our PV array and our DC link capacitor is done. Now we have to convert this DC to AC voltage. Okay, so for that I'm taking universal bridge, and we have to take a number of these arms as 2 because we are dealing with single phase, and it will be IGBT diode, and it's okay, but we have to format this and rotate this block to left and right. Okay, so this is our DC link voltage, and it's okay. Now we have to add filter. Okay, so I'm taking another series RLC branch, and in this case similarly I will use the same LC filter here I used in my previous video. You can check this, and it will be 8.2 E minus 3, and inductor will be 2.18 E minus 3. Okay, so basically I'm using the same LC filter I used in my previous video. So it will be series RLC load and nominal voltage 240, frequency 60 Hz, active power I want it as 10 and it will be 0, and capacitive power as 5 watt. Okay, so control R, and I need AC voltage source which will act as a grid in this case. So peak amplitude will be 240 and square root 2. Okay, because this is for 240 volt RMS single phase and 60 hertz frequency. Okay, so everything is okay. So this is our LCL filter, and this is our grid. Okay, so everything is done. Now we have to measure the grid voltage and grid current. For that we need voltage measurement block, and go to tag. It will be VGrid. Okay, tag visibility will be global. Similarly we need to measure the current here. Okay, so this is current measurement block, and it will be I gate. Okay, so it's okay, so B grid and I grid is done. So here our main structure or model is done. We have our PV model, and then a DC capacitor, then inverter, and then filter and the gate. So this is called a single phase um, grid connected PV array. Okay, so here um, we need MPPT controller here. Okay, so I have already made my MPPT controller here, so I'm copying this one, Control C or copy it, and you have to paste it here. Okay, so this is the MPPT controller, and you can take a snap or you can rewrite this function here. So this is the MPPT controller for this model. So you can take this snap or you can rewrite this one by pausing the video here. Okay, so this is the MPPT controller here, and we have to sorry, we haven't, so it will be MES PV. Okay, and we need bus selector block here. Okay, this is V and this is I. Click OK. Okay, so this MPPT controller will give us the reference DC voltage. Okay, so this is giving the reference DC voltage, and from this on we have to generate the gate pulses for the universal bridge or inverter here. Okay, so here we have our reference DC voltage, and here we have to generate the gate pulses for the inverter. For this I'm taking a subsystem block here, so we have to take the input here from the MPPT controller, and this will be VDC reference. Okay, so this is our DC reference voltage, and we will deal this later. And we have our DC voltage which is VDC, so we have to take a mean here. So this is our VDC, so we have to take a mean block here, and it will be our initial output I want it as 420, and sample time as TS power it's okay. And go to block, and it will be our VDC main. Okay. Okay, so okay, and now we have to we have our main model, and we have to basically generate the gate pulses for the inverter part, and we have our gate voltage and gate current. Now we have to convert this gate voltage and gate current into DQ frame. Okay, for that I'm firstly taking the gate voltage here, so it will be V grid, and I want to deal with the per unit quantity. Basically for that I have to convert this grid voltage into per unit quantity, so we have to divide this by 1 divided square root 2 multiplied by 240. Okay, so it is okay. So then we need a PLL block here. Okay, so this will give the frequency and omega t. So this is for frequency f, make it global, and this is omega t. Okay, this is omega t, and we have to convert this figure into a DQ format. Okay, so as from previous video, I will similarly use a fundamental parallel driven block here. Okay, so we have our frequency here, we have our omega t, and this is our input. Okay, and in parallel driven the built-in values. Okay, now we have to use the sample time as stage control. Now here the angle is in degree format, so we have to convert this to radian. So we have to multiply this pi divided 180. Okay, so then magnitude angle to complex, we have to choose this one because we need real and imaginary part, and then complex to real imaginary. So and then we have to use max block here, so this real and imaginary part is our final VDVQ format. Okay, so this is VD and VQ. Okay, make it global. So in PLL driven I have set this take sample time as stage control, so it's okay. So we have our grid voltage in per unit quantity and in D and Q format. Okay, similarly I have to choose the grid current here. Okay, so it will be I grid. Similarly I have to convert this one into per unit quantity. Okay, so for that 240 divided by 3500 and square root of 2. This value will convert this current into per unit quantity. Okay, so similarly from this current we have to convert this to ID and IQ format. So for that I'm taking a subsystem block here. Okay, and here this is I grid. Okay, and frequency and omega t. Okay, okay, so here similarly I will use the alpha beta 0 to DQ format here. So for that we need this frequency one for this current, and I will use saturation block here. and maximum frequency I want as 70 and lower limit as 40. Okay, and then we have to delete this to get the beta. For that we have to take a math function, and then it will be reciprocal. Okay, because we need time, and here we have taken the frequency, so it will be reciprocal, and click OK, and gain will be 1/4, 1/4, and then we need discrete variable time delay. Okay, because we are using delayed version of 1/4 to get the beta. Okay, so this is the delayed portion, and discrete variable time delay sample time will be ts control. Okay, now this input will be the igrid, and then we need max, and max input will be 3. Okay, so this is our alpha part, this is the delayed part, which is the beta, and for 0 plus obviously we need a constant block of 0. Okay, so this is 0, and this is our alpha beta 0, so we have to take alpha beta 0 to dq. So this is our alpha beta 0, and this omega t is here. So we have our dq 0, but we want to deal with only the dq portion, so I'm taking a selector block here, and this index will be 1 and 2 basically. Click OK. So this is our IDIQ. Okay, so this is IDIQ, and tag visibility will be global, and similarly I'm taking a out block with the same name. Okay, so we have our gate current in IDIQ format. So at this test it's okay. Now we have to generate the reference current. Okay, so here we have already our VDC reference here, so this will be used here. Okay, and from block, and we have our VDC mean. Okay, so this will be our VDC mean. Click OK. So from this VDC mean, it will be minus plus. So from this VDC mean we have to subtract this VDC reference, and then we have to similarly convert this to per unit quantity, which is 1 divided by 400, and then we need a PID controller. Okay, and it will be P and I discrete time, and this one is VDC mean. Okay, so TS control, this will be PI, and sample time I haven't checked this, so it will be RTS control, and it will be 12, and integral portion will be 200. Okay, so everything is okay. So this will give the reference current in D format. Okay, so this is ID reference, make it global, and we are dealing with ID IQ. Okay, so I'm taking a constant block here, and its value will be 0, and we have to max this to get the ID IQ. So this is our ID reference, and this is our IQ as 0. Okay, so this is our IDIQ reference value. Okay, so this is IDIQ reference. Okay, so we have our VDVQ and IDIQ and IDIQ reference. Okay, so from this we have to regulate our current. So I'm taking a subsystem block here. Okay, to regulate the current. Okay, so this is IDIQ. Okay, then we need this IDIQ reference to in the current regulator, or we can say it as current regulator. Okay, so then from we need IDIQ reference, and at lastly we need this VDVQ. So from Control C, and it will be VDVQ. Okay, so we have to here I will use the feed forward control here to regulate the current uh, in smaller portion. Okay, so from this IDIQ we need to add subtract block. So from this IDIQ reference, the main IDIQ will be subtracted, and then we need to feed this to a PID controller block, and it will be PI, and the skip time and sample time will be TS control. Okay, and it will be 0.15 and 6.6. Okay, and then similarly we need another add block. Okay, so before that we have to use the feed forward control. So I'm taking dmax block here for the both IDIQ reference and VDVQ. Okay, and two add block will be needed here. First one will be plus plus minus. This is basically I'm implementing the feed forward control equation here. Okay, so this will be plus plus plus. It's okay. So this is VD and this is VQ. Okay, so then we need to add some gain block because of our filter. So this will be 002, and this is for this one, and 0.2, this is for this one. Okay, okay, this 0.2 will be here, and this is for IQ, and 002 will be used here, and this will be similarly IQ. Okay, so this is for D and this is for Q. So we have to max this one because we are dealing with D and Q format. Okay, okay, now this is our converted VDVQ. Okay, before that I want to take a saturation block here, which will give upper limit as 1.5 and lower limit as 1.5. Okay, so this is for converted VDVQ. Okay, so this is VDVQ converted format, and tag visibility will be global, and Control C, and I'm taking a out block from this one, and this will be a VDVQ. Okay, so this portion is done. Now we have to generate a reference signal. Okay, for that I'm taking another subsystem block. Here a VDVQ converted, and then VDC mean will be needed here. So I'm taking from block here, and this VDC mean, control V, VDC mean, and lastly the omega t. So this will be from, and omega t, and this is the omega t. So okay, and inside this one we have to firstly deal with VDC mean. Okay, so VDC mean, we have to compare this VDC mean with the AC 240 volt RMS. Okay, so it will be our RMS plus was 240, then SQRT and 2. So this is the peak voltage, and this VDC will be divided by this one. Okay, and this VDVQ converted again. This is basically for the reference reference generator or reference signal generation. Okay, now here at this stage we have in D and Q format. Okay, so now we have to use dmarks here to get the real and imaginary part here. So the first part is the real part, and the second part is the imaginary part. So from this one we need to real imaginary to complex form, and then complex to magnitude angle. Okay, complex to magnitude angle. So this is the final value. So this is the magnitude here. So before putting the angle we need this omega t, and add this omega t with a constant. So this is for optional because I am using a compensation here because of the control part. Okay, so 2 pi or frequency of 60 hertz, and for the control part this will give us this. Okay, so we have to add this angle and this portion, and then we have to feed this to sine and this one. Okay, so this is our U reference, so our reference signal to generate the gate pulses. So this will be our U reference. Tag visibility will be global, control C, and I'm taking out block here. Okay, so our reference signal is generated. Now we have to use this reference signal to get the gate pulses. Okay, so from this one we need a PWM generator 2 level. Okay, so it will be for single phase, and frequency I want it as 5e3, and sample time as TS, power and everything is okay. Now I'm taking a go to block, so it will be gate. Okay, so this gate will be used for the universal bridge or inverter. Okay, so everything is okay. So this is our final model. We have our PV array, our inverter, our filter, and gate. Okay, so this is a single phase grid connected PV array. Okay, and here I am taking the grid voltage and grid current here. So this is V grid, and this is I grid. Okay, now let's add a scope. V grid and I grid. Okay, let's reduce the stop time as 0.5. Now let's run the model to check whether it's working or not. Okay, I think everything is okay. Okay, now it's working. Yeah? So let's uh, run the model again. Now you can see the current is okay. Now let's change to 500. Now you can see the current is decreased. Okay, so our current controlling is okay. We can ensure this one. Our current is okay, and at this stage I want to measure the TSD of our current. Okay, let's add a scope here to iGate and data logging, log data to workspace, structure with time, and it's okay. And under modeling and model setting, we have to change some setting to get the TSD. So it's okay. And now let's run the model again, and after a TSD calculation I will use the variable irradiance here. Okay, for accurate TSD measurement, as we have taken this as our constant or our base, so we can get our reference TSD at 1000, then we can check the other irradiance value. Okay, okay, so the curve is okay. Now we can check the TSD here. We have to update this, sorry. So here we have some transient. Okay, so 0.2 second is enough to give the TSD, and fundamental frequency 60 Hz is okay. Now let's compute it. Now you can see the TSD is about 1.04%, which is very less value. Okay, so it's quite a good model, you can consider it, which is below 1.5%, so it's great. Okay, so our TSD is okay, model is working. Now let's change the constant irradiance value to variable. For that I am taking a stair generator block. Okay, and it will be 0.5 and then 1, then 1.5. Okay, so amplitude, let's take 1000, then 800, then 600, and then 500. Okay, 550, no, 500. Okay, okay, so 1.5 means 1.7 is enough. So now let's run the model and check whether it's working or not in a variable irradiance. Okay, so it will take some time. Let's wait for this output. Now you can see, so up to point, now there's some, take some time to finish it. Now you can see up to point 5, the current is about 20. Okay, so up to 0.5 second we have reduced the irradiance value, current has decreased. Similarly, up to 1 second to 1.5 second, current has lower limit and then very low. Okay, so by this way we can confirm that our model is working in a variable irradiance. Okay, so that's all for today. We have successfully made our grid connected PV array single stage, obviously. Okay, so that's all for today. Thanks for watching, and if necessary information is needed, I will put this in the video description. And so thanks for watching. In the next video I will show you um, three-phase grid connected PV. Okay, and the next I have some plan on covering videos on vehicle to grid or grid to vehicle and so on. So that's all for today. Thanks for watching. See you in the next video.